Yes, sir.
Okay. So now we come to the particle in the box, because the particle in the box is a case where the second derivative has an infinite discontinuity, right? So let's look at the potential in detail. So it has three regions: the left region, the middle region, and the right region, right? So let's call this, say, region 1. This is region, say, 2. And this is the potential, say, V of x. This is region 3. And let's color the region where, the particle cannot exist with yellow, right? So let's write down Schrodinger equation in these three regions. So in region 1, we have right. Right. Okay. So let's look at, say, region 1. So region 1 is d squared psi. The wave function is psi 1 dx squared minus 2m by h squared v 0 minus e. Okay. So v0 is infinity. So, but it's hard to work with infinite potentials, right? Your equations don't make sense. So, but we want to know, what we are doing here is that we are saying, okay, let's keep the potential finite, say v0, and then solve the equation, and then take v0 to infinity. Okay, that's what we're going to do. So if I do this, then and the energy, we look at the energy of the particle to be less than V0, right? Because in the limit where the potential energy V0 goes to infinity, whatever the energy of the particle is, it won't be infinite. It'll be always less than V0. So we want to see that. So that means that, this thing, V0, is greater than E. Sorry. Let me plug my iPad to the laptop so we don't lose our work. Wait. Okay. So, yeah, trust this computer. Oh, don't trust it right now. Okay. So, so let's define K1 to be a constant, which is a positive constant, and it's 2m V0 minus E over h bar squared square root. Okay. So then essentially what we have here is the square of this constant. And here there should be a psi 1, right? So this is an equation you should be able to solve. And this equation is just given by psi 1 of x is given by, there are two linearly independent solutions. One is A, or let's call it, say, let's call it, yeah. So one is A, e to the power minus I, not I, because it's going to be exponentially decaying or exploding, plus B, e to the power plus K1x. Okay, you guys know this, right? Because if it had the opposite sign, then there would be i's here, right? But here we are looking at the decaying solutions. Okay? You guys know how to solve this, right? This is just very, yeah. This is one of the most simple differential equation because you have psi, and you know that, if you have, a function which is equal to itself after taking two spatial derivatives, it has to be some linear combination of exponential functions. And because of the sign of this thing, you can show that there's a minus sign and plus sign. Okay. Now, if I take x going to minus infinity, that means if I go in that direction as far as I can, we would expect that because that particle, in this region, the particle has imaginary kinetic energy, right? And therefore, we would not expect that particle, we would expect the particle, also we want to have a particle where the wave function is normalized. So if I look at these two solutions, if I take x going to infinity, then I see that x going to minus infinity, then I see that this guy is going to diverge, right? So this means that on physical grounds, I have to set a equals to 0, okay? And therefore, we see that in region 1, for V naught finite, we get an exponentially damped solution, right? This x here is negative. But if I take V0 to infinity, then what happens is that, this factor becomes arbitrarily large. So for negative values of x, there's any value of x, this goes to 0, right? So in the limit, V naught goes to infinity. Thus, we see that in the limit where V naught goes to infinity, the wave function must be 0 in this region, right? The wave function is 0 in this region. Does that make sense?
Yes, sir.
So by similar logic, the wave function must be 0 here as well. Okay? So in the middle region, we have the solution of this guy, of the equation, is going to be simply, V0 in the middle region is 0, right? V is 0. So if I define K to be square root of 2me over h bar, then in the middle region, psi 2 is simply going to be given by a prime, some constant, e to the power I, kx plus b prime, some constant, e to the power minus I, kx, right? Okay. So now what we want is that, we know that this is continuous. So continuity implies that if I take psi of 2, which is a function of x, and put x equals to minus L by 2, this is going to be 0. And that, because this is equal to the wave function in region 1, right? This is what continuity means. So this is going to be 0 because this thing is 0. And similarly, if I take psi 2 and put x equals to plus L by 2, and this is equal to psi 3 at x equals to L by 2, which is also 0. Okay? So if I look at these two conditions, then what do I get? I get is a prime e to the power minus I k L by 2 plus b prime e to the power plus I k L by 2. This is the first equation. And the second equation is a prime e to the power I k L by 2 plus b prime e to the power minus I k L by 2. And this equation, we can write this as a matrix of exponentials e to the power minus I k L by 2, e to the power I k L by 2, e to the power I k L by 2, e to the power minus I k L by 2. Now this is acting on a vector a prime, b prime, and that is equals to 0. So we want a non-trivial solution to this equation. That means that the determinant of this matrix must be 0. So, and if I write that out, then it means that it's going to be e to the power minus I kl minus e to the power plus I kl must be 0. And this means that sine of kl must be 0. That means k of l must be n pi, where n is an integer. Okay? So if I now go back to my value of k, my value of k was 2me square root by h bar. So I just square it. Let me just square this for convenience. So here I have h squared in the denominator, and here I have l squared. So this is n squared pi squared, right? So this we can rearrange and write it as e of n is n squared pi squared h bar squared divided by 2ml squared, okay?